When we're doing double integrals, we did the double integral over dA. When we let the function, if you will, that we're double integrating be 1, so we don't really have a function other than 1 here. What we saw was that gave us the area of D, didn't it? Whatever D, this double integral, we're integrating over whatever two-dimensional area there in the xy plane. Well, if we just did the double integral of 1, the function being 1, that gave us that area, that D, we call it. Well, if we do the same thing with the triple integral, say we're doing the triple integral and we usually call it E, that we do the triple integral over, but we just do the triple integral of dV, or in other words, 1 times dV, guess what that gives us? That's going to give us E, which now the term would be a volume, right? So it's analogous there, 3 dimensions, that if we just do the triple integral over 1, for 1, the function being 1 over surface E, or that particular shape, better way to put it, I guess, but that's going to give us the volume of that thing. Okay, so that's one use here. We can use it to calculate some, call it not very nice, in some cases, volumes. Okay. So here's our first venture here. All right, so find the volume of the region below x plus y plus z equals 8, and above the xy plane. Oh, and above the region in the xy plane trouble writing here. Above the region in the xy plane, bounded by x equals 3 halves square root of y, and x equals 3. I'm having trouble writing thing. X equals 3 halves y. All right, so yeah, so this is usually this phrasing right here. All this right here, that's usually describing what we call region E. Okay. However, in this particular case, I'm not doing a triple integral over this region of some function. I just want to find the volume of that. Okay, so this is my E right here, being described by from here to here. All right, you with me? And so I just want to find the volume of that region E. And so that's why we talked about that. So we're just going to do the triple integral 1 dV. I just have to figure out, how to describe E in terms of X's and Y's and Z's. Well, got a good start here for X's, the X's and the Y's. Probably, yeah, let's start, let's just graph the XY plane part here, because it won't be hard to figure out the Z, I don't think, but yeah, and we've we've got nice little functions. We're not as used to functions of y as we are functions of x, but we got functions of y here. This one, let's start with this one. That's just a line, right? Not in our normal y equals mx plus b form, but it is linear. However you want to sketch that. Of course, it goes through 0, 0. And then if y is 1, x would be 3/2, 1.5. So one way to get it. This one, x equals 3/2 y. Again, we're talking, if I go at it this way, we're used to y equals in a function of x, so we have to do that. That's fine. If I have y equals the square root of x, that's think there. But if I do x equals the square root of y, which is I just multiply that by 3/2. It kind of reflects it around and things, but yeah, you get it goes more like that. So this is more like we've got here. Like I said, you can however you need to figure that out. But here's what comes out looking like. It turns out that that's a good point, because that's where those I should grab this little. All right, so if y is 1, we'd have x is 3/2. Y is 2, 4. We would have 3/2 times 2, that'd be 3. X is 3 minus 4. Oh, that is right. Okay. Yeah. Okay. So this region right here is what I want to take that region above it, so above the XY plane there. So let's see. So I need to set up this triple integral. So what do we see happen? Now, obviously here we want to, since we've got the x in terms of the y's, we want to do the z's first, because z, I can get z in terms of x and y, one way to look at it. What is this right here? X plus y plus z equals a. It's just a plane, right? It's not any kind of fancy surface. So I want the region below that and above in the xy plane. So what I want here, so I want that the z, well, if you're talking about the xy plane, that z equals 0. So I'm going from the xy plane up to that. I mean, it's above this, but you see that, so the z's would start at 0 and go up to this, which, of course, I would want that in terms of z equals, so it'd be 8 minus x minus y. And so that pretty well lines out your z's there. Do those first. So 0 to 8 minus x minus y. Like I said, we're doing 1 is our function, if you will. Now dv, the order, like we said, we're going to do the z's first. There's 6 different possibilities for dv. You can go dz, dx, dy, or dz, dy, dx, dy, dz. Well, we lined it out, we got dz. Now what would be next, you think? Well, unless we switch things around here, we've got x in terms of y's. And so the x's are next, because they're in terms of the y's. And so which one's the bottom one? Well, it looks like the curved one, which is the square root one, 3/2 squared y. To the linear one, 3/2 y. Which obviously then, these are y's, so what do the y's go to? Well, it looks, by mine, it looks like, we should verify, but it looks like it's 1. Y equals 0 to y equals 1 is what it looks like to me. We can verify that if we just set those equal. Yeah. If you divide by 3/2, get rid of 3/2. You got the square root of y equals y, which is going to be square both sides. Y equals y squared, which is subtract the y. Yeah. Y minus 1. So that's 0 and 1. That's what I get. Sound okay? You believe that? All right, so go ahead and finish this off. The lovely triple integral times 3, right? Just thought integrals were bad, now we got to do 3 of them. All right, so 0 to 1. We'll just remember those, put those in here. So yeah, when we do the first one, like I said, we're just doing the integral of z, of 1, so dz. So that part's nice anyway. So just be z, and then we're throwing in z for those limits. Okay, so now we have, well, it'll just be 8 minus x minus y. Z is 0, 0, so part's not that bad. So now we've got this integral, right? Dx, so we're doing the derivative with respect to x, so what do we got there? 8x minus 1/2 x squared minus yx, because the y is a constant just like the 8 in that particular case. And then the x's go from 3/2 squared y to 3/2 y. So we've got to plug those in for x. All right, so we finally got to the fun part here. All right, so plug in 3/2 y, so that'd be 3/2 y, 8 times 3/2 y minus 1/2 3/2 y squared minus y times 3/2 y. Okay, then we have 8 times 3/2 squared y minus 1/2 then 3/2 square root of y squared, and then minus y times 3/2 square root of y. So that's the hardest part, I believe, of this. So that'll be 4y, 4 times 3y, so that'll be 12y. That would be 1/2 times 9/4 y squared. That's 9/8 y squared. And minus 3/2 y squared. And then this will be 12 square root y. And that'll be 9/4, but the square root of y is, square root of y squared is just y. 1/2 times 9/4, so that would be 9/8 minus y. And then last but not least, y times 3 halves squared y, so that's 3 halves. Y to the 3 halves. Putting things together here, I've got, what would that be, 12 eighths, 21 eighths, y squared. And then here I have 12y, and then minus 9 eighths, so it'd be 12 minus plus 9 eighths, y. So that's 13. 96, 105 eighths. Check that. 12 plus 9 eighths. Right. Sounds right, 105. Right. Yeah, I get some fractions going here. And then, what's left? I did that one, those two. All right, so I got minus 12 squared y, and then a plus 3 halves, y to 3 halves. So last but not least, do that, which is just some power rules. It'll be 21 eighths times 1/3 y cubed. And luckily this is 0 to 1, right? Plus 105 over 8 times 1/2 y squared minus 12. Let's see, that'd be y to the 3 halves, so times 2/3. And then plus 3 halves, that would be y to the 5 halves, antiderivative. So it'd be 2/5 times that, and then 0 to 1, thankfully. So that's 7 eighths. Because plug in the 1, you got 1s for the y, and then zeros are going to be zeros. So this is going to be 7 eighths plus 105 over 16 minus, this will be 8, and that'll be 3/5. I think that's what I got. So yeah, just figuring out the fine details there. Oh, well, that's not very much. Which that's probably true, because this is not a very big area right there. 3 over 8 is what I get. 3/8. Any problems with that? Anything? Find anything there? It's Monday, so. Wouldn't expect that. We figured maybe some errors to be made. All right. So that's one example here of using this to find volume. And the other one is another interesting, I think anyway, problem. So let's do that one also. And that is this one, find the volume. Because this one also has a little review built in here too. It's never a bad thing. All right, so find the volume of the tetrahedron. With vertices 0, 0, 0. 1, 1, 0, 0, 1, 1, and last but not least, 0, 1, 0. Four-sided tetrahedron pyramid, in a word. Yeah, so just for fun, let's to draw this one out. So we got vertices 0, 0, 0. X is 1, Y is 1, Z is 0. So that would be here in the XY plane, 1, 1, 0. And then 0, 1, 1. So X is 0, Y is 1, and then Z is 1. So you have that up here, and then 0, 1, 0, X is 0, Y is 1. So that would be the other vertex. So kind of connect the dots here. Put a little exercise. Yeah, so you got this. It is a pyramid looking little shape there. Over there. So yeah, you got the base here is that little triangle. Maybe it's kind of hard to visualize, but I can kind of see it. All right. So how do we do this? Well, kind of like the one we just did. If we do that triple integral over, so if I do the triple integral, this is kind of my region E right here. We'll call it dV. If I can get that set up, 1 dV, that'll give me that volume. I'm going to do it anyway. So we're going to kind of do it the same way. The problem is here, I have no functions. I've only got points. But we are going to kind of approach it the same way we did that first example, in that I'm going from, it's above the XY plane, so I'm going from the XY plane up to basically this little surface right here, which is the plane. So Z is going to go from that XY plane, Z equals 0, up to that plane with vertices. So what are the vertices of that plane? 0, 0, 0. That's 1, 1, 0. And then that upper point, that's 0, 1, 1. With me there? Believe that. That's what Z would go between. And so that's what I was saying. This is where a little bit of review kicks in. How do we get a plane with 3 points? Well, what do you need for a plane? You need a normal vector and a point. Well, we got 3 points. Probably I'll choose this one, right, for my point. But I need a normal vector. How do I get a normal vector? Well, the normal vector is the perpendicular vector to it. So this has got a lot of good review here. And how do I get, though, the normal vector for the plane? Well, you need to come up with a perpendicular vector out of that plane. And how do you get a perpendicular vector? Cross product? Yeah. All right, so the normal vector, I need 2 vectors in this plane. All right, so so we'll do the cross product of 2 vectors. And again, nicely, we've got 0, 0, 0 is one of the points. So if I get a vector off of that, or you just subtract the x, y, z portion. So that vector would be 1 minus 0 would be 1, 1 minus 0 would be 1, 0 minus, basically just converting that to a vector. And then the other vector in that, that we could do if we did this one and this one. So 0 minus 0, 1 minus 0. Right, remember all that. So do the cross product, which we did it with the determinant that. It's all coming back to me. All right. So the I would be times that determinant of that. So it'd be 1 minus 0 minus then the J, cover up that one. So it'd be 1 minus 0 also there for that determinant. And then the K is cover up that one. So you got 1 minus. Works out pretty nicely. I don't know that the one that you'll have to do for the homework does quite that nice, but yeah, did that for mine. I minus J. Don't always try to do the easiest one, but I did a pretty easy one here. I'll admit. Okay, so that's my normal vector right there. That vector would be normal, or let's call it what, 1, negative 1, 1. The other way to write it there. All right, so how do we put that together then for this plane? Well, remember these are the, and then like I said, I'm going to use, so here we go. It's 1, negative 1, 1. That's my normal vector. Then 0, 0, 0. Use that for my point. So remember how you do it? You do this. This is the x from the vector. This is the, or the I component, or the x component, whatever you want to call it. That's the point. Remember what you do? You do the 1 times the x minus the x value. And then you do minus, then the y's components, call it. So it'll be y, negative 1 times y minus 0. And then 1 times z plus 1 times z minus 0 equals 0. So again, not too bad. So it'll be x minus y plus z equals 0. Aha! So that's my plane with those vertices. I need terms of z, so let's just call that z equals minus x plus y, or y minus x. So that's what z goes between. All right, now, then I need to figure out in the xy plane, since it started with z there, now I need to look in the xy plane, see what I got there. What do I have in the xy plane? Well, it's this triangle right here. But how do I get that? Well, you just kind of do the xy's 0, 0, 1, 1, 0, 1, 0, 1. So yeah, you got those 3 points would be the xy plane points. See where I got those? I just did the xy's instead of the xyz's. So yeah, that's my xy area, the D area, I guess you might call it. We've been calling it. Let's go, Leah. So the last one we did, the x is second, and then the y is last. Let's do it the other way, just say we did it the other way, okay? We could do it either way here. We could do the y's and the x's, but it might be easier to do y's this time. But all right, so, or the x's again, but let's do the y's. So I want to go from this y to this y, so that's, what's that line right there? Well, you go 0, 0, 1, 1. That's just y equals x, isn't it? Slope is 1. And then this line right here, well, that's just the horizontal line, y equals 1. So wouldn't the y's go between x to 1? With me there? So I go from this line, which is y equals x, to this line, which is y equals 1. And then the x's, well, the x's are easy because they just go 0, 1. So that's doing it. The second part here, let's get over here. So my area is going to be, so we again are starting with the z's. Z's go from 0 to this, negative x plus y. Then we said we're going to do the y's next. So the y's go from x to 1. And then the x, last but not least, go from 0 to 1. How's that sound? And then it's probably, this is easier one than the previous one. Yeah, so do the z's first here. So just z, and I can pitch on here. When you do that, yeah, it's just going to be this minus that, so negative x plus y. Plug in the limits. Now, second one I'm doing with respect to y, so be minus xy. Now I'm doing this one. So I have the integral then of minus xy plus 1/2 y squared. And that limits go from x to 1. I integrate with respect to x. I get that figured out. With me? So far so good? So plug in, these are the y's, so plug in these for y. So it'll be minus x times 1. 1/2 times 1 squared, so it's 1/2. Fortunately, this one's not 0, it's x, so plug in the x for y, so it'll be minus x squared, and then plus 1/2 x squared. That's pretty nice. So all it really simplifies there, we've got minus x plus 1/2. Yeah, this actually, if you combine those are like terms. I guess you have to, but if you do, that would be, those combined would be minus 1/2 x squared, but we got a minus out there, so it's actually plus 1/2 x squared, isn't it? Nothing else combined, so we're ready to integrate that, so that'd be minus 1/2 x squared plus 1/2 x. That would be plus 1/2 times 1/3, so it'd be 1/6 x to the third. And nicely, this one is 0 to 1. So we get minus 1/2 plus 1/2 plus 1/6. Again, I probably did that. That was a nice example. You could. 1/6. All right.